One of the most powerful techniques used to probe the cosmos is spectroscopy. Put simply, this technique allows analysis of incoming light after it has been separated into its component wavelengths by passage through a prism. In the same way that sunlight is broken into a rainbow of colors, wavelengths, by droplets of water. With appropriate decomposers and amplifiers, the same technique can be extended to non-visible kinds of electromagnetic waves such as ultraviolet, infrared, or radio waves, even of very low intensity. Substances present in outer space act as filters that absorb radiation of certain characteristic wavelength, colors of their equivalent. In consequence, the absorbed radiation are found to be missing or attenuated in the recorded spectra. Alternatively, certain wavelengths may be enhanced by emissions from energetically excited substances. In many cases, the substances causing the absorption or emission can be identified from the spectral patterns, which serve as fingerprints of the substances involved. The analysis of microwave radiation, the kind that at much high intensities heats ovens, has turned out to be particularly fruitful in this respect. Spectroscopic probing has revealed that the cosmic spaces are permeated by an extremely tenuous cloud of microscopic particles containing a number of potentially biogenic molecules, mostly highly reactive combinations of carbon, hydrogen, nitrogen, oxygen, and sometimes sulfur or silicon that would hardly remain intact under Earth conditions, but could give rise to biologically significant compounds. This presumably happens in the formation of comets, long seen as fiery objects hurtling through space while scattering a stream of sparks behind them. Comets really consist mostly of dust and ice loaded with variety of organic compounds. This has been learned by spectral analysis, and thanks to the recent passage in the Earth's neighborhood of the famous comet discovered in 1681 by the English astronomer Edmund Halley, by direct chemical tests with the help of instruments carried by spacecraft. Even more solid is the evidence brought to us by meteorites. For example, the Murchison meteorite, which fell in 1969 in Murchison, Australia, was found to contain a number of amino acids remarkably similar in nature and in relative quantity to those obtained by Miller in his experiments. This kind of evidence, while providing a considerable boost to the significance of Miller's results, tells us further that organic compounds can survive the scorching crash of celestial bodies through the atmosphere. There is thus ample evidence that a number of biogenic compounds can form spontaneously under primitive Earth conditions in interstellar space and on comets and meteorites. Most likely, such compounds provided the first seeds of life. How much was made locally, how much was brought in from outer space is still widely debated. The Belgian-born American astrophysicist Armand Delzem from the University of Tolda believes that virtually all the building blocks of life, as well as all the terrestrial water, were carried to the Earth by comets and that contributed to the final accretion of our planet. According to Miller, on the other hand, the chemical precursors of life were formed mostly on Earth itself.